This is another video in the series from Math 1073 for UTSA. Today we'll be talking about Module 4.1, division of polynomials. So we have a few examples here, and I notice that the first thing I notice is that for all of these, the divisor is linear in all these cases. That's not necessary. You can divide higher degree polynomials, but we're just starting with simpler examples. We may at a later time need to do examples that are a little bit harder. So, real briefly, I want to do a quick review of just long division of numerals, or numbers, I should say, because maybe you haven't done that in a while. So let's say I wanted to do something like, I don't know, 819 divided by, let's say, 12. Okay, so get started by doing my 12 divide into 819, and we're not going to get a decimal answer. We're going to have a remainder, right? So the first thing I should look at is comparing these two digits to these two digits. How many times can I subtract 12 from 81 without getting into a negative value, right? Without passing 0. So that's going to be 6 times. 6 times 12 is 72. So I'll put a 6 up here above the 1, right? And then I'll multiply the 12 and the 6, and then put the result, the 72, below the 81. So 72, right? And then I'm subtracting. And I usually, when I'm doing this, for whatever reason, I'm doing long division by hand. I usually don't write the minus symbol. I know that I'm doing it, but I typically don't write that. Then I subtract, and we get 9, of course, and then I bring down the next digit, the 9. So I'm comparing two digits with two digits. In some cases, like if the remainder had been different, we might need 3 digits potentially. Just depends on how things go. I think in this case, though, we'd have to basically, like if we had 11 at this point, we'd have to go get another digit. Well, if the numbers were bigger and 12 doesn't go into 11 at all, then you need a third digit, right? But for now, we're comparing two digits to two digits. So how many times does 12 go into 99? Well, that would be 7 times, right? 7 times 12 is 84. No, 8 times. Yeah, 8 times 12 is 96. So I'll put 8. 8 times 12 is 96. And I can subtract, and I get 3. So my remainder is 3. So this equals 68 is the quotient, and 3/12, which, of course, we could reduce that. I'm not going to right now, though. So 3 is my remainder, 12 is my divisor. And if I think about it, the way mixed numbers are written, really there's a plus here. This is 68 and 3/12, right? So there's just sort of a hidden plus that we don't typically write when we write a mixed number. So basically, there's the process. Well, I'm going to do the same thing over here with these numbers, or these polynomials. So I'm going to do x minus 1 divide into x squared, x squared plus 5x minus 1. And much like previously with the 12, I was comparing two digits to two digits. Here, I'll compare two terms to two terms for similar reasons. And I don't know if any of these examples are going to do this. I assume one of them will. If we have a missing, oh no, there is one that does this, right? If we have missing terms, like if we didn't have a 5x there, we'd have to put in 0x. So the linear term is represented. But I believe there's an example like that we'll get to in a minute. So, in particular, the 5x doesn't really play a role here in the decision-making process of what's the quotient. I'm going to compare the leading term to the leading term. And essentially what you do is you take the leading term in your dividend, and you divide it by the leading term of your divisor. So x squared over x, okay? That's the pattern we're going to see. And this is, of course, x. When you divide that out, so I'm going to put an x up here above the 5x, above the linear term. Basically, I'm going to keep the linear terms in a column. They're organized by degree, essentially. All right, so now I'm going to multiply x times x minus 1 and put the result below those two terms, kind of like the 72, the way the 72 came about. So x times x is x squared, of course, minus x. And then I'm going to subtract, and I'm going to put parentheses to remind myself. And as with the numbers, I typically will not write the minus sign. When I'm doing this for myself to get something done, I won't write the minus sign. I'll just know that I'm subtracting. And as long as you basically pick a method and go with it, either write the minus or don't. You probably should not write it sometimes, but not others. Just pick one and go with it. And as long as you know what you're doing, You don't have to write the minus. Okay, so now I add down, well, subtract down. So x squared minus x squared is 0, naturally. Kind of like over here, we have nothing in front of the 9. If we can achieve that, we want to reduce as much as possible. And then I'm going to subtract 5x minus negative x. I'm really adding because of the double negative, so I get 6x. There we go. And we're not done, but if that all made sense, then you know how to divide polynomials more or less. There might be some, you have to be careful, right? If it's larger degree, there's more steps. But if that all made sense, that's it. That's the concept. There's not a whole lot more to it than that. Anyway, now I can bring down the -1 and then play this game all over again and say, okay, we'll take this leading term, divide by this leading term, which would be 6. So that goes up here, plus 6. And then we take the 6 times the x minus 1 to get 6x minus 6. Okay, and then I'm going to subtract. So we get, when we subtract down, 6x minus 6x is 0, of course. -1 minus -6. I'm really adding 6, so I get 5. Okay, so there's my remainder. So the result, and I would like to put it here, but I'm kind of out of room, so I'll put it down here. The result is x plus 6 plus 5 over x minus 1. That is the result, okay? Sometimes you don't need, is the problem? Yeah. Right answer in the form quotient plus remainder over divisor. Yeah, okay. There may be times where you, depending on the problem, what you're going to use this for, where you don't need this result, but sometimes you do. Sometimes you really just need the remainder, or you really just need the quotient. It depends on the situation. I will point out in Cal 2, just recently, we had to do this. There was a type of problem called a partial fraction decomposition, and we need to be able to divide polynomials in order to solve the problems in Cal 2. So this is something you will definitely use later, if you're taking Cal 2 at least. Okay, so let's go do another one. So here, basically same thing. Take x plus 3, okay, and then divide that into, let's make that longer, 5x squared plus 10x minus 17. I'm going to change the stylus to be smaller. Okay, so compare two terms to two terms. I take the leading term here, divide by the leading term here, and I get 5x, right? 5x squared over x will be 5x. So that I put right here over the linear term. I'm keeping the terms organized in columns by degree. If we go back over here real quick, you'll notice that, oops, wrong button there. These are all linear, and these are all constant, right? There's no x's in that third column, and there's no x squares in the blue column. Okay. So now I'm going to take 5x times this, get 5x squared plus 15x, and write that below those two terms. 5x squared plus 15x. And then I'm going to subtract down, so I get nothing, which I could put as 0 or 0x squared if I want, but I'll just leave it blank. So 10x minus 15x is negative 5x. Bring down the minus 17. And again, take this leading term, divide by that leading term, and get negative 5. So minus 5. So then multiply negative 5x minus 15. Yep. Subtract down. So I get nothing. Negative 5x minus negative 5x would be 0. So negative 17 plus 15 would give me negative 2. So this equals 5x minus 5. And I can either put plus or minus here. I can put the minus in the fraction or put it in front. I'll put it in front. So minus 2 over x plus 3. Okay. All right, next example. Yeah, this one, notice that in the dividend, there is no linear term. There's no like 2x or 5x or whatever. So here's what we did. I'm going to start the same way, x plus 1 divide into, and I'll do negative x squared plus 0x. I have to have a placeholder. And you might wonder, well, why? What's the role of the placeholder? Well, if you had something like 809 divided by, I don't know, 7 or something like that, right? Would you do 7 divided into 89? Well, the 0, 0 is nothing, right? You don't need it. But of course you do, right? If you leave that 0 out, then you're missing most of the quantity, right? So you need a placeholder. That's what 0 does. In this case, we don't typically write plus 0x when we're writing a quadratic expression or quadratic function. We don't have to necessarily all the time, but in this case of doing long division, we do. If we don't have it, things get all messed up. If you wanted, it would work. It would work just fine, I guess, to have a blank spot. As long as, remember, because I'm keeping the columns aligned, you have to have a column for linear terms. So you could leave it as a blank spot, but it's probably better just go ahead and say, well, 0 is the coefficient for the linear term. Anyway, a little short on rooms. Let's adjust it. Okay. So, as usual, compare two terms to two terms, although the second term here doesn't really do a whole lot in determining what the next step is. Take the leading term, divide by the leading term here. So negative x is the result. So minus x, and then multiply that with the divisor to get negative x squared minus x. Then I'm going to subtract. So I get nothing, and then I get, pause the video and think about, what do I get here? What goes here? Well, since I have 0 minus negative x, I really have plus x. Definitely be careful to pay attention to when you have a double negative, if you're subtracting down, and especially if you have a longer problem, more terms. It wouldn't, I don't know, it would be easy to forget that you're subtracting and just make a mistake. Just be careful with that. Then I can bring down the minus 1. And I'm drawing the arrow every time. You don't need to do that. Just write the negative 1 where it's supposed to go. So now I'm taking this leading term, divide by that leading term, I get 1. So plus 1. So then multiply that with the divisor, x plus 1. And then I can subtract down 0 and minus 2. So this equals negative x plus 1 minus 2 over x plus 1. Okay. All right, next example. So this one, notice that this is a cubic polynomial, right? Degree 3. I don't have a quadratic term, so I have to put that in. So we'll do a 3x minus 1. And you might have noticed so far the leading coefficient in the divisor. In the first two cases, I think was 1. In the third case, it was negative 1, and now we have 3. So we might end up with fractions at some point because of this 3. So 9x cubed plus 0x squared minus x plus 2. Okay, and again, I got two terms here compared to two terms here. Okay, so I'm going to take this leading term, divide by that leading term. So 9x cubed over 3x will give me 3x squared. And I put this over the quadratic term because I'm keeping them aligned in columns. So then I can multiply that term with the divisor. I get 9x cubed minus 3x squared. And I can subtract down. So I get 0 here, but I'm not going to write. I'll leave that blank. And then 3x squared, because we have 0x squared minus negative 3x squared. So we're really adding. And then I can bring the x down, so minus x. And then again, take this leading term, divide by that leading term, I get x. So plus x, and then multiply x against the divisor. 3x squared minus x. Subtract down, and oh, we get a big old nothing, right? It cancels entirely. That can happen sometimes. So I'll pull down this 2, and that's my remainder. I don't have, there's nothing to eliminate here. The linear column is done, essentially. So that means that this equals 3x squared plus x plus 2 over 3x minus 1. Okay? So that's it for long division. I think the next thing is synthetic division. Yeah. For the following exercises, use synthetic division to divide. So synthetic division has some limitations. You'll notice that all of these examples, all of them so far, well, let's put it this way. Okay. So for all of these, all the divisors are linear, right? Degree 1, all of them. And as I said, it's not necessary. You could divide a cubic by a quadratic, you can definitely do that. But notice that not all of these are monic, right? This one, oh, I misspoke. I said a moment ago that this one had a linear coefficient of -1, but that was incorrect. They were all 1. This one has a linear coefficient that is not 1. It's 3, right? Which is why I said we might end up getting fractions here. These, all of them, are monic, meaning that the leading coefficient is 1. For synthetic division, that's not essential, but basically synthetic division becomes very complicated if you try to use it to divide by a non-monic linear factor, so, or divisor, I should say. So like 3x plus 1, you can do it, but it becomes a bit of a pain. Also, synthetic division can be used to divide by higher degree polynomials like a quadratic, but that is quite complicated, and it's something you really would not want to do. If you were dividing by a quadratic, you'd follow the same pattern here, and you would just do long division. You would not want to use synthetic division. Anyway, what is synthetic division? It's the name implies, it's division, but somehow not somehow processed or packaged somehow, right? Synthetic. So basically, here's what you do. You look at this divisor and think, okay, what is a 0 of that divisor? What would I plug in for x to make that 0? This would be -3. So I'm going to write -3, and I'll put it in a little box. There are different ways to set up, to do the setup part. I'm just going to do the way that I'm accustomed to doing it. If you've seen it before and there's a slightly different way of writing it, that's okay. Some people will do, I guess another version looks like that, I think, but I prefer just the box. So then I'm going to take all the coefficients in the dividend and put them in order. Just the coefficients, though. So 1, -4, 4, 3. And if I was missing a term, I'd put a 0. Then I'm going to have a line below that. Okay. Now, basically, the reason this works is somewhat complicated. I'm not going to go into why this works. That's something we could do in a live session if someone wants to know. It's not that it's difficult. It's just tedious and kind of complicated. So I don't want to do it here. Anyway, this first number I'm just going to bring down as though nothing has happened to it. Okay. Now, in order to start the next column, I need to put a number here below the -4. In order to do that, I'm going to take the number at the bottom of this column, and I'm going to put it here, but I'm going to multiply by the number in the box when I do it. So 1 times -3 makes -3. Okay, and then I'm going to add down. So I get -7. All right, and then in order to go to the next column, I need to put something here. I'm going to take this guy and put it here, but I'm going to multiply it by the number in the box when I do it. So -7 times -3 makes 21. So 21, I'm going to add down. And then take this guy, put it here. But when I do it, multiply by the number in the box. So -75. And then add down, -72. So this last number, this is my remainder that I would have gotten had I done long division. These numbers are the coefficients of the quotient. So this guy equals x squared minus 7x plus 25 minus 72 over x plus 3. And essentially what happens is, if you were to do long division and synthetic division side by side with the same problem, but do the two methods, you would see these same numbers, right? These same numbers right here would be showing up, and these numbers would be showing up in both solutions. They would show up in a slightly different arrangement, but this basically achieves the same arithmetic, right? All the arithmetic we do here with multiplying and subtracting, this procedure performs that arithmetic, but you don't have to write all the x's out. It's a sort of a bare bones procedure that gets the job done, and it's not necessarily as clear why. That's the part we're skipping for now, but it gets the job done. So you might want to go and do this problem with long division and check that you get the same answer, and check that you do in fact see these same numbers show up. Okay. So next example. So looking at the divisor, I'm going to say, oh, well, 3 is what I would plug in to make that into 0. So I'll take 3, put it in the box, and I'll take the coefficients here. So 3 minus 13, 8 minus 22, and then have my addition line. Bring the 3 down. There's nothing to do to the 3, so it's sort of like you put a 0 there to start with, but I think of it as just bringing it down. And then I will move this 3 here, but multiply by the box when I do it, so I get 9. Add down, move over here, multiply by 3, get negative 12, add down, and then move this over here, multiplying by 3 when I do it, so I get negative 12. Again. So I just started feeling like I might have made an error. So I'm just double checking. Yep, I don't see any mistakes. Okay, so minus 34. So that means that this equals 3, kind of out of room here, but I'll try to squeeze it in. 3x squared minus 4x minus 4 minus 34 over x minus 3. Okay. Okay, let's go do the next example. I think there's only 2 left. Yeah. Okay, and this is the same thing. I look at the divisor. What would I plug in to make 0? In this case, that's 1. So I'll put 1 in the little box, and then I'll write the coefficients from the dividend. So 1, 0, because I'm missing the cubic term, minus 3, 0, because I'm missing a linear term, and then 1, the horizontal line. Start by bringing the 1 down, and then multiply up into the next column. So 1, add down, get 1. Multiply up, I get 1, add down, negative 2, multiply up, negative 2, add down, negative 2, multiply up, negative 2, add down, get negative 1. Okay, so this is going to be, you might wonder, okay, yeah, that's great and all, that's the coefficient, but what is the degree of the term? Basically, just like when you have something like, say, a squared times a cubed, that's a to the 5th, the exponents add together when the bases are the same. If you have a to the 7th over a cubed, this would be like a to the 4th, right? You subtract the exponents. So this is degree 4, this is degree 1, so the result is degree 3, okay? Another way to look at that is these numbers give me the coefficients of the quotient, and they're always in descending order. So since there's 4 of them, it goes 3, 2, 1, 0 for the degree. So that's another way to see what degree you should be using. So this will be x cubed plus x squared minus 2x minus 2 minus 1 over x minus 1. Okay. And same thing. So negative 2 would be my 0. So negative 2. Put that in the box. Negative 5, negative 13, and then 0. Okay, there's no linear term, and then 11. And then I can bring down that negative 5. Multiply up, so I get 10. Add down, I get negative 3. Multiply up, so I get 6. Add down, I get 6. Multiply up, I get negative 12. Add down, get negative 1. So I get negative 5x squared minus 3x plus 6 minus 1 over x plus 2. There you go. That is synthetic division. As I said, you can you can use long division to divide any 2 polynomials that you want. Obviously, well, perhaps obviously, we're not going to have like decimals somehow with polynomials. So if you were to divide a polynomial by one that has a greater degree, there's just nothing to do. You can't really do that. But any polynomial combination where the dividend has a higher degree than the divisor, you can always do that with long division. Synthetic division only works. It only works in a straightforward way when you are dividing by a linear polynomial, right? To degree 1, and especially if it's a monic, the leading coefficient is 1. If you have a leading coefficient that's not 1, you still can, but it becomes more challenging. And if you want to divide by like a quadratic, it becomes quite a bit of a pain. You would really rather not do that.